an Poisson from gravity and many sides. He's written a couple of very great textbooks, Relativist Toolkit, and then Gravity with Will. Today he's going to tell us about resonances in binary inspirals. So Eric, please take it away.
Thank you, Bill. So thank you very much for the invitation to be here today. So I've been at CITA many times, but not so much recently. And it's always a pleasure to be here. And I want to tell you about stuff that I've done not so recently. And the reason why I like to talk about this is because I think the physics is really fun. And really fun to talk about. And also for me, who's mostly a GR type person who talks about G mu a lot, that's probably the closest thing I've ever done to real astrophysics. And because of that, I'm very proud of it. I like to tell people who are astrophysicists, I consider myself to be a failed astrophysicist. And I told that to Scott Tremaine once. And to make me feel better, he replied that he was a failed relativist. So that we can all even that. Now, the danger in coming here and to talk about astrophysics is that, if I break it down here, I know there's some experts in inertial modes here. That's you. That's you. There might be experts in gravitomagnetism. There's definitely going to be experts in resonances, and there's going to be experts in binary inspirals. So I'm open to a lot of flack from you. And I'm guaranteed to offend everybody. So that's the danger I place myself in, but why not? It's fun. I want to explain all the words in this title, and I want to tell you all about that. And I will be very disappointed if you don't interrupt me with questions. So please do that as soon as they come up. It's going to be a lot more fun for everybody if it's actually a dialogue. Okay, so the context is binary inspirals. So I really, the big picture for me is gravitational wave astronomy and the fact that now we have routine observations of mergers of compact binaries. So that's going to be my first member of the binary. That's going to be the other one. And I don't really care about that one. It could be a neutron star, it could be a black hole. I don't really care. What I want this star to be, that's going to be my main star in the binary. I want that definitely to be a neutron star. And I want that to be a rotating neutron star. That's going to be very important for the story I want to tell today. So it's going to be a rotating neutron star with some frequency omega that I'll pin down in a few minutes. There's orbital motion, of course, and because of the orbital motion, there's emission of gravitational waves. So this system emits gravitational waves pretty much in all directions. And because of that emission of gravitational waves, the binary system loses energy gradually. So we have this inspiral that proceeds until the two stars merge. So if I were to plot something like orbital frequency as a function of time, we would find that this keeps on increasing until, formally it goes to near infinity as the stars, start touching one another. That will happen for me at t equals 0. So the merger occurs at t equals 0. And the timescales I'm interested in here are roughly something like, 300 seconds, something like that. So something that can be summarized in minutes. And the range of orbital frequencies I worry about is, roughly 20 hertz, let's say 10 hertz to basically 1,000 hertz. Because those are the frequencies for which, that's the range of orbital frequency for which we get gravitational waves that happen to lie within the frequency band of gravitational wave detectors like LIGO, Virgo, and Tidal. So that's the kind of picture, and we have now routine observations of those gravitational waves. So what do we learn in those waves? We learn about the orbital motion of those things. We don't learn very much about the merger itself because the merger occurs at too high a frequency for that to produce waves in the right frequency band. So we have access to the last minutes of inspiral, but we don't see the merger directly. For that, we need the high frequency gravitational detectors. All right. One aspect of the orbital dynamics here that I want to focus on is the tidal interaction between the two. Because, you know, if the objects were very far apart from one another, we could neglect the tidal field that one exerts on the other. But here I don't want to do that. I want to actually focus on that tidal interaction. And that just goes to say that, you know, because of the tidal field exerted on, say, this one by that one, the star will tend to deform a little bit. That one will tend to deform a little bit. And that will modify the orbital motion. It will modify the details of this process over here. And that's something that also can be imprinted in gravitational waves. And that's, you know, a very exciting, you know, thing to pursue in gravitational astronomy. But what I want to do here is to do even more than that. I want to exploit the tidal dynamics in the production of resonances so that we'll have something even more dramatic than just a gentle tidal interaction that just modifies this in a rather gentle way. So what I have in mind here is this, and I want to, you know, hopefully convince you that there's a distinct possibility in gravitational wave observations to measure a resonant effect. What do I mean by this? Well, I mean what we normally mean by resonance. Something will be very, very much amplified because of a matching between the natural frequency of an oscillator and a driving frequency. So that's the story I want to unfold. And I'll tell you that the oscillator is going to be a whole bunch of inertial modes. The driving force is going to be the tidal force exerted on this star by the other one. But it's not going to be the good old Newtonian tidal field that we, you know, normally think about. It's going to be something slightly more exotic, namely having to do with gravity produced by moving masses, mass terms, as opposed to just static masses. So I'm going to unravel all of this. So first of all, what do I mean by resonance? Well, I just meant what I just said. So I'm going to tell you how we can think of neutron stars as a whole bunch of oscillators, but let's go back to the picture of a harmonic oscillator. So if you have something driven by an external force, you know that something will happen when you're driving the oscillator with the right frequency that's, you know, that happens to be out, that happens to be the natural frequency of the oscillator. You have this phenomenon of resonance. So we're going to look for those matching frequencies, the matching frequency between the oscillator and the driving force. So I have to identify that matching frequency and you know, tell you about the oscillator picture. But the idea here is that we're going to produce large amplitudes in something that has to do with the internal physics of the neutron star. So that's where my oscillators are. They correspond to internal motions of the neutron star, and I want to basically drive them to very large amplitudes. And that's the resonant effect when we have the matching frequencies. And as a result of this, what we're going to have is a situation where I'm putting a lot of energy into the internal motions of the neutron star. So that comes with a large and, you know, increase in energy, something that happens rather suddenly in the time scale of the Inspirals. So we're going from 30 seconds to just a few seconds. I don't remember exactly what that time scale is, but that's basically that. And that large energy has to come at the expense of something. And the only source of energy that's available here is the orbital energy. So that large energy comes with a rather sharp decrease in the orbital energy of the system. And that will translate into a rather sudden decrease in the radius of the orbit. So the orbital radius will decrease, you know, suddenly if you decrease, you know, if you take energy away from the orbit, that translates into a decrease in orbital radius, and that, you know, that translates into a, you know, corresponding large increase in orbital frequency. Increase the radius, you increase the frequency. And what's interesting for gravitational wave astronomy is that if you have this rather sharp, you know, change in the orbital frequency of the system, you have something similar happening in the frequency of the gravitational waves, and that will drive a dephasing of the gravitational waves. And what I mean by that is that suppose I have two models for the gravitational waves that come out of the system, one that doesn't account for this effect. It would produce a phase evolution that describes the normal chirp that we normally deal with in gravitational waves from compact binaries. But let's compare that to another model that accounts for those effects, because we're changing in one model suddenly the frequency of the gravitational waves. We're also changing the phase of that model, of the phase of the wave in that model is going to be shifted with respect to the other one. And because the phase accumulates over time, we're going to generate a rather large or substantial phase shift. And that's really the name of the game in gravitational astronomy. Gravitational wave detectors are very sensitive to large, to phase effects. And the fact that, you know, a resonance like this is something that can produce cumulatively in time, this dephasing that we can go and measure. So bottom line is that, you know, if you have a resonance like this, then you can hope to see the effect of gravitational waves through a dephasing of that nature. And that's something that can be measured. And through this measurement, you can learn about what produced the resonance in the first place.
But the tuning of the resonance still not back on gravitational. When you pass through the resonance, they go on.
Yeah. So the dominant effect is still the gravitational wave speed.
So the nonlinearity of the that's it's a second order effect of the duration of the resonance.
Yeah. So what Chris is saying is that, well, we still have an inspiral and it proceeds almost like it used to, except that as a sort of added effect, you have one sudden transition that occurs, and you drive through that resonance because of the dissipative effect of the whole thing, because of the emission of gravitational waves. You drive through that resonance in a time, you know, that's comparable to this, beyond seconds. Short. So what I'm trying to say is that, you know, you don't stay at resonance, you drive across the resonance because of the overall emission of gravity. Clarifying that. Okay, other questions like this? Sure. Yep.
I guess related to that, to get to a large amplitude and then we'll have a large effect, you need to stay on resonance for a relatively long time, that you transfer energy, but you have to drive
Right. So yeah, so it's not instantaneous, of course, and so there's a time scale associated with passing through the resonance. But what matters in the end is how much energy has been transferred from the orbit to the internal motions of the neutron star. That's, you know, that transfer of energy is really what gives you a measurement.
Right. It's a maybe this is because I don't know if I'm updated in like the electric types. But my understanding is that the time scale is where you can stay on resonance. Like you couldn't ever get that one.
Right. So yeah, so let me go into that a little bit later when I identify the modes. Okay, so I'm really thinking of my neutron star, you know, as a whole bunch of oscillators, and that seems a little bit strange. But you know, as I keep telling my students, everything in physics is a harmonic oscillator, and you go through your life in physics discovering how true that statement is. And you know, every time you learn something new, you find a new application of this idea that everything is a simple harmonic oscillator. So the general statement is this: if you have a system that's at equilibrium, well, it's not an oscillator. But if you try to describe what happens to it if you perturb it away from equilibrium, then regardless of the nature of the system, the departure from equilibrium is something that can be described in terms of harmonic oscillators. The analogy is very complete. So in the case of a neutron star, I'm talking about the fluid inside. And for me, who's not an expert in neutron star astrophysics, my neutron star is a perfect fluid. Sorry. Don't want to offend anybody, but that's what my neutron star is. And I want to look at the fluid motions in this limited approximation where it's perfect fluid. And I have the rotational motion of the star, but on top of that, I'll have departures from that equilibrium state that are being driven by the tidal field exerted by the other one. And what I'm saying here is that those internal motions in the fluid those departures away from the equilibrium state is something that I can describe in the language of fluid dynamics in terms of a normal mode analysis. So I look at all the possible ways that the fluid can move if it departs from the equilibrium, and I can identify all the independent modes of vibration, associated with my rotating neutron star. And what I'm saying is that each mode will behave as a simple harmonic oscillator. So eternal motions are being described in terms of normal modes. And each one of those normal modes behaves as a grid oscillator. So I'm sure you've done, regardless of your level of physics, I'm sure that you've done analyses like this. Maybe you started out with a whole bunch of springs linked together, and you identify all the collective motion of those springs and identify those as normal modes. You can look at the motion of the guitar string, and that will behave as a superposition of normal modes. It's the same thing regardless of the system you look at, and it works exactly the same in the case of a perfect fluid. So what we have are a bunch of normal modes, so those are the departures from equilibrium that are being driven by the tidal interaction between the two stars. And what I want to build up, again, is the story that some of those modes will become resonant at some point during the end spiral and produce some very nice effects. So we're going to push over here. I'm sorry if it becomes less visible to you guys. Okay, so let's talk about normal modes. Of a neutron star, at least idealized as a perfect fluid. And I'm going to distinguish between rotating stars and non-rotating stars. It's important for my story that my star be rotating. So I'll explain why, in just a second. But let's start with non-rotating stars first. So when we're dealing with a non-rotating star, we can identify all the relevant modes, and they come, with some nice names like S mode, P mode, G mode. Maybe there's some others that I don't know about. And when you look at the physics of normal modes of vibration, typically the basic question you want to answer is: so if you have a mode as an oscillator and you push it in one direction, what is going to be the restoring force that brings it back to equilibrium to eventually set up this oscillatory motion? And in the case of the normal modes of non-rotating stars, if we talk about F or T or G modes, the restoring force is basically gravity and pressure. In various combinations, they usually act together, but some modes gravity might win, those are the G modes. For other modes, pressure might win, those are the P modes. But typically it's a combination of both of those, and then you have a whole slew of modes. And the next question that you would like to answer about those modes is: what are the frequency? What kind of eigenfrequency do those modes come with? And here the answer can be complicated. It really depends on the model that you have for the interior of your object, whether you have stratification, whether you have all of those issues. But just to make a very simple picture, I will claim that for non-rotating stars, there's basically one scale of frequency that the star gives you, and the modes will come with that scale of frequency. The scale of frequency, if I write it down, it's going to be a combination of the two scaling factors that the star gives you, namely the mass and its radius. Throw in a gravitational constant, throw in the square root, and you have something that dimensionally has the dimension of frequency. And therefore, something by dimensional analysis will give you necessarily the scale of frequency for any mode that you might find inside the non-rotating star. Those are the only scales that are available. But of course, the numerical, number that the numerical factor in front can vary, and in fact, it can vary substantially. But let's leave it at that. If you work this out, that's about 2 kilohertz if you're dealing with a one solar mass neutron star, and a star that would have a radius of, say, about 10 kilometers. I'm largely making this up here, but those are the typical numbers. And the point is that you get frequencies for those modes that are very high frequencies. And the problem with that is that it lies well outside the variable frequency band, which means that those modes play a role, but they'll never get into resonance because you'll never match the frequency. So the idea here is that to match the frequencies, you have to have a mode frequency, namely an oscillator frequency, that matches the frequency of the driving force. The driving force is produced by the tidal field. The tidal field has a frequency that's equal to the orbital frequency. And if the orbital frequency is always lower than the mode frequency, which is the case here, you'll never get a resonance. Now, there's a lot of fine print to the statement that I just made, because you're experts, you would know that. You don't achieve resonance, but the approach to resonance can have significant effects in gravitational wave models. And that's something that people have started to incorporate in, LIGO templates and such. So even though we don't achieve resonance with the F mode, for example, which is the lowest, lower frequency of the spectrum, the approach to resonance still has an effect, but we don't achieve resonance. If you really want to push me on this, the G modes do get resonance because they typically come with much lower frequencies. But I'll talk about that a little bit later. The driving force turns out to be very small in those cases. So the standard expectation is that the G modes, even though they become resonant, they don't have a dynamically important, impact on the resonance.
I'm going to ask about the crust. If it's not perfect fluid,
Right.
and you say you have like crystalline crust, what kind of frequency is crust level?
So that's a good question, to which I don't know the answer. I have some colleagues who have studied the modes that are generated because you have an interface between the fluid core and the sort of more solid type of crust. Interface modes, and those can be at interesting frequencies, very much along along the ones that I'll get for inertial modes. So in the hundreds of hertz. So that's interesting. The crust itself, I don't know. I would suspect it's also high frequency.
But you want to have, for example, electromagnetic signal. That's
Oh yeah. So
that's the move you want. So
right.
there's a real possibility. You can cross up and not.
Yeah. So it's going to brighten. It's going to give you a ER signal. Yeah. So all of that.
But the function of gravitational wave signal, the crust is probably some down.
At least that's my understanding, but it's very perfect. I don't remember seeing anything that suggested that the crust is interesting. But
You had a really low mass response. It's crust. This would be very big, strong, thick crust, large crust mass. It's probably not going to be realistic.
yeah, and it may not change the scaling, but not change the numerical factor, but not the scaling. So, yeah, so the scaling really tells you that the typical modes are not things that will become resonant. That's the message I want to convey, even though it might be simplistic. I think it's still very active. All right, so that's why I wanted rotation, because if I turn on the rotation of the star, I have access to new modes that you don't get without the rotation. And those are the inertial modes that are talking. So we still have all of those modes, and they get corrected. The frequencies get corrected by having factors having to do with the centrifugal deformation of the star. But that doesn't change the scaling that I talked about before, so it doesn't really alter the picture here. But the important thing is that the rotation gives me new modes that we don't get without rotation, and those are inertial modes. And those are really interesting modes. And I'm not going to do a very good job at describing what they are, but I will try. Here's what they are. So the other modes that we talked about are basically pressure waves or gravity waves or things like that. So they come with a fluctuation in density and pressure and gravitational field, and they're very familiar in the context of what we know sound waves or gravity waves on top of like something on top of water. So I mean, we're pretty familiar with those. Inertial modes are completely different. So when we think about them, and it's going to be a crude description of them, but it's you know, it's still pretty good. Unlike those modes here that come with fluctuations in pressure and density, but almost no fluctuation in velocity, here we have the opposite. They come with a fluctuation in velocity, but almost no fluctuation in pressure or density. So basically, they're velocity modes. A velocity wave that is superposed on top of the rotation velocity of my rotating star. So it's like a velocity modulation on top of the existing velocity. So it's basically a fluctuation in the velocity vector, and correspondingly, we get some, but very little fluctuation in density and pressure. I know the units don't match here, but I'll just write it like that. So that's one characteristic. So it's basically a velocity mode. What's the restoring force? Well, here we were talking about gravity and pressure as the thing that restores the oscillator to its to equilibrium. Here we're dealing with something very different. So if I move to the co-rotating frame of the star, so I'm going to look at the mode in that co-rotating frame. Because I'm in the co-rotating frame, we know that we have, inertial forces like Coriolis and centrifugal that get added to our description of what's going on. And because I'm working to leading order in the rotation, centrifugal deformations don't really matter, but Coriolis does. Remember what Coriolis is? It's a V cross omega type force that you get because you're working in that, frame that's not inertial, but rotating with the star. So they're restored by the Coriolis force. So the physics is completely different from those. And because the physics is completely different, the eigenfrequencies that come out from for inertial modes turns out to be completely different, and in particular, completely divorced from that scale over here. The eigenfrequency in this case is a numerical factor that depends on the distribution of mass inside the star, but it scales with the angular velocity, velocity of the spinning motion. So that's the rotation rate of the star, multiply this by some numerical factor over the unity, and you get the mode eigenfrequency. So now we're starting to be in business. I want to tell you a little bit more about what I'm assuming for my neutron star. I'm going to be assuming that this rotation frequency, the spinning frequency of the star, I want it to be around 100 volts, which is pretty fast, but it's not crazy fast. And there's some millisecond pulsars out there that, satisfy this. But if I have that, that's my request to the universe to produce that for me, a rotating neutron star that happens to be of that frequency in a binary system with an orbital frequency that's also in that regime. If I have that, I have an eigenfrequency, a mode frequency, an oscillator natural frequency that happens to be comparable to the orbital frequency, namely the frequency at which the tidal forces are driving my pulse. So I have the possibility during the inspiral at some point to hit a frequency, say 100 hertz, let's say, at which that inertial mode will be compressive. I have the matching frequencies. So that's why I needed the rotation, Therefore, that's why I needed the inertial modes to have a situation where we can have comparable frequencies between the driving force frequency and the oscillator frequency. That's, that's a condition we need for resonance.
So technical question, in this context, as the realistic composition structure of the neutron star, you put in computation of the neutron.
By others, not, yes.
So it's not just that above. Relying
So
it's that.
yeah. So some people have done a lot of work doing this for realistic models of neutron stars. I didn't. Again, it will change the numerical factor. It can change it by quite some time, quite some factor, but it's not going to change the overall scheme. That you can get how to improve your model. I can promise you my model. No, it's a very good point. The hardest part is to do it in full VR. So there's been some work on that. But the numerical task is a lot more difficult in the GR setting than it's. Okay. Other question? Yep.
Well, you assumed, nature give you this frequency.
Right.
But of course, the other process, which is tidal synchronization, will also spin up the new.
Right.
So somebody must have done the calculation. It's synchronization efficiently enough that the spin frequency, which is going to serve a bomb with the orbital frequency.
Yeah, there's been some work on this, and that goes back many years now. And the conclusion seems to be that the tidal interaction doesn't produce synchronization. So that doesn't, that would take too long. Much longer than the inspiral. So I think what would need to happen for this to happen is that the neutron star would have to be spun up at some point during, suppose if we have a binary evolution that lasted all this time. It was spun up maybe by mass transfer at some point. And then, it stays there until the merger.
So there's no.
But the double pulsar is.
It's there. It's there. Yeah.
Yeah.
So if we can wait for that double pulsar to fall into the LIGO band, then yeah, that's
nice cycle. But from spinning out from this frequency, you don't need a huge amount of cycle to make it spin that time longer than.
Right. That's
It looks like also mass on the game here.
sorry, I missed.
Millisecond also mass the game here, 5 frequencies instead of
Right.
revealing the cycle.
Yeah. So basically, I'm counting on you. Tell me how this can happen. We're good. Yeah. Good. So yeah. So I'm asking the universe and medias. Okay, so now we have, pretty much all the pieces of the story. So we have the possible, so we've identified the need for inertial modes. That's to have the right, the hope for a frequency match between driving force frequency versus mode frequency. That, of course, produces the resonance. So we've got that, we've got that. So the only part of the story I haven't told you about is this. So now I'm going to add, that to the picture and tell you why I needed that in the first place. So rid of this. So we get a resonance if we have matching frequencies. So that we seem to have, we're good with this. But it's not enough, right? So I'm only get a resonance if I have a non-zero driving force. And in the context of my fluid motions, a driving force is something that I would get from the tidal field. So the driving force is produced by the tidal interaction, the tidal field exerted by the other star. But in this language of fluid modes as harmonic oscillators driven by something, what matters here is not that we have a driving force, is whether that driving force has a non-zero projection against that mode. So what I really mean by that is that, I have a mode amplitude called Q. And that mode amplitude satisfies an equation that looks a lot like the equation of a driven harmonic oscillator with its natural frequency. So N would be a mode label, Q is the mode amplitude, 2 dots is the time derivative. And what I need on the right-hand side is a non-zero driving force for the oscillator. And the way that this is constructed, when you work out this theory in the fluid mechanics of all of this, is that the driving force is actually an integral between the tidal force density, rho is the mass density inside the star, and to that you have to include in the integral the mode eigenfunction. Because the mode comes with an eigenfrequency, but also an eigenwave function, which is basically the description of this independent mode of vibration that each mode gives you. And you integrate this over the volume of the star, and you get the driving force that lives on the right-hand side of that oscillator equation. And here's the bummer of the whole story. So there's going to be a couple of twists. The bummer is that even though I have the modes, even though I have a match of frequencies, if I plug in a tidal force that's produced entirely by Newtonian gravity, namely a gradient force that comes from a potential, to leading order in the description of the mode where I neglect all second order terms in omega and I keep only leading terms that are linear to omega, I find that for Newtonian gravity, that overlap integral vanishes. That's a theory. And it simply has to do with the nature of the mode eigenfunction and the fact that in Newtonian gravity, the tidal force is necessarily the gradient of something. So that would be true in Newtonian gravity. And that means that even though I have the ideal condition to produce a resonance, what I'm missing here is an actual driving force that would drive the oscillator at resonance. So the whole story unravels. Doesn't work. But I wouldn't be giving the talk with it. This was the end of the story. And it's not the end of the story because fortunately for us, gravity is not Newtonian, gravity is general relativity. And the beauty of GR is that it gives us other types of gravitational interactions that are not just Newtonian. And that's where gravitomagnetism comes in. And I'm not going to develop the story very much because it can get technical pretty fast. But I'll just say that when we go from Newtonian to GR, well, we're going from a Newtonian potential that gives us everything, a scalar function that tells us everything about gravity, to my favorite thing to talk about, GU. And that is something that has 10 components in it. So we have a much richer description of gravity in GR. Now, if we break this down, we can break this down into a time-time component. And it turns out that the time-time component of the metric tensor in GR is very strongly analogous to the Newtonian potential. So it basically does the same thing. So if we only had a time-time component to the metric tensor, we would get Newtonian gravity, the leading order. But we have more than this. We have time-space components of the metric, and then we have space-space components of the metric. And those are new things that we don't have at all in Newtonian physics. And the nice thing about this here is that it's very much analogous to a vector potential in electromagnetism. And in fact, when you work this out, in a weak field, slow motion type approximation, you find that this component of the metric tensor behaves pretty much exactly like a vector potential in electromagnetism. So it has a very similar, governing equation. It produces a field that's very much like the B field in electromagnetism. And that B field, that's now purely gravitational, produce forces that are like V cross B type forces that are very analogous to magnetic type forces in electromagnetism. So what I'm saying here is that because we have those additional ingredients in the description of gravity, we have a new type of tidal force that's analogous to a V cross V, namely V cross the curl of the vector potential. That's also present in the description of the tidal interaction between my two stars. So it's a relativistic effect, so it doesn't occur at Newtonian order. We're talking about post-Newtonian gravity here. But the essential aspect for us is that this new type of tidal force is not a gradient of anything. And because of that, that theorem that I quoted before doesn't apply. And because of that, we now have a driving force. So in relativistic gravity, we have a driving. So just to summarize this, so GR gives us something that looks like a vector potential. So that's gravity that's produced by mass currents, like the B field in magnetism. Instead of charge currents, we have mass currents. So we have this new type of field that comes for free in GR. That new field gives us a new type of force that's very much like the V cross V type force in standard magnetism. But because it's not a gradient like we had in Newtonian gravity, this integral that used to vanish no longer vanishes, which means that when we go back to the mode equation, we now have everything we need. We have a non-zero driving force, maybe a little bit smaller than we thought because it's a post-Newtonian effect as opposed to Newtonian. But now we still have a tidal field, a gravitomagnetic tidal field, that is, changing in time with the orbital frequency. And we have a situation where in the course of the Inspiral, we can match the orbital frequency with the mode frequency and establish resonance. And as soon as we have that, we have a mechanism by which we can dump a lot of the orbital energy into the internal motions of the star. That that corresponds to a loss of orbital energy, corresponds to a sharp decrease in orbital radius, sharp change in orbital frequency, dephasing of the wave, and now we have. I think I'll spare you the details of all of this and how it works out in numbers. We're still talking about small numbers, but we're talking about a small dephasing in gravitational waves that is not perfectly accessible. But I think there's a shot that this would be accessible for LIGO in the a sharp configuration that is just a
So are you finding this is a stronger effect than a couple of G modes?
I think so. I think the G modes give you a very, very tiny dephasing because the overlap integral is so small. At least that's the law that came out of it.
So here there are this expression for the omega r of the C, right? But that's a massive suppression in the overlap.
Yeah, the main difference is that the G modes oscillate like crazy. So the overlap integral vanishes. So you have a mode eigenfunction that oscillates a lot, so the integral never builds up. Those inertial modes are very, very gentle functions. So they do something. So let me take the thought, and then I'll be done. So what I'm saying here is that when we combine the gravitomagnetic tidal forces with the inertial modes, we have the possibility of resonance. And then it's a matter of exploring how many modes can become resonant during an Inspiral, and I found that 4 of them do become resonant. Those are the ones that give you a substantial overlap integral like this. So it will occur first around, say, 50 hertz. It will occur then around 100 hertz. I mean, the numbers here depend on what I've assumed for the rotation rate of the star and the numerical factors that come to this calculation here, so they're not to be taken literally. But the point is that there are 4 distinct inertial modes that will become resonant in the course of an Inspiral, and each one will produce its own gravitational wave dephasing. So in principle, each one could be measured individually. And the beauty of this, if it can really be pulled off, is that if we can measure at which frequency those resonances occur, and in principle, that's information that's accessible in the gravitational waves, those frequencies are really a diagnostic of the internal structure of the neutron star. That number over here is very sensitive to the distribution of random cycling. And here, through those resonances, we obtain very, very valuable information about the internal composition of neutron stars, something that's very hard to do, even in conventional astronomy, even with standard tidal physics here by the time. So I find that prospect very exciting. What I haven't worked in here, and I'm hoping that people like Phil will pick this up one day, is to really tell me if this can really be done at the level of individual resonances, or whether we have to live with some kind of cumulative effect of all four as one compounded, effect in gravitational waves. And then the answer will depend on whether we're talking about A sharp or whether we're talking about cosmic explorer or third generation gravitational detectors. I'm convinced that when we're there with the third generation detectors, that will become accessible. And I'll stop here. Yes.
I think even the Newtonian limit is not exactly zero. There is
No, that's
there's
right.
a V over Sansky square term.
Yeah.
Which is, so I'm curious, how's that term compared to your GR term? So your tidal force is now smaller by V over C or V over C squared?
It's so it's two factors. So there's the orbital velocity, and then there's the rotation divided by C squared. That's the suppression factor.
So the Newtonian may still have some chance of.
It's possible. So I didn't look into that. But yeah. So to get something on zero, the Newtonian description, you will have to involve a mode description of the high order model.
There's a possibility.
Yeah, so that's what it is. And
That's V over C squared, C being Sansky.
oh yeah, okay. So yeah, so that's an interesting.
Values of the presence, how do they change the discipline?
Okay, so I mean, to the linear order in omega, they just scale with omega. Right? So it's just a numerical factor. In front will change depending on the mass profile.
And so all four frequencies scale.
Yeah. So that's right. So here I calculated those numerical factors, making some crude assumptions about the mass profile, and I've scaled those numbers with the 100 hertz. That's my fiducial rotating the stars. So use that.
And so over the course of the Inspiral, what's the typical value of the
So you really want to between those. So the dephasing scales all sorts of things like the radius of the star, the masses, and all of that. It scales with the spinning rate, so you can adjust all of those things. With assumptions about this, you get an overall numerical factor in front of all of this that ranges from 0.02, which is too small, to around 0.2, which is small but plenty large. The answer depends on the relative orientation between the spins and the orbital angular momentum. Some modes are really happy with this orientation. Some modes are really happy with this orientation. And then typically it's a trade-off. If you have a random orientation, you get different amplitudes from the form.
Well, the reason it's quite good is that I think it can definitely also affect the current.
Well, I think it's still small for the current state.
Oh, well,
like it's not crazy.
Yeah, I mean, I think the rough expectation is that if you have a S0 signal, then that would be based on 0.1.
Right, that's right.
So 0.5, 0.2 is. So,
But this is also a dephasing on top of other dephasing that we don't know. Exactly.
Right.
of course, yes.
Right.
Yeah, that's
But, you know, I would agree with the statement. It's already probably important to model this.
Yeah.
Can we separately extract?
Oh,
other
yeah,
effects?
that's what.
Yeah.
What's the non-memory? And then everyone is there any important scale of negative momentum. What's going on?
So, yeah, so I won't be able to answer your first question because I forget I forget what that number is, in terms of, amplitude and velocity. So there's certainly an exchange, so I talked about the loss of orbital energy, but of course that also means also angular, sort of angular momentum, but really, here in orbital angular momentum. There's also a torque that's going to be acting on the spin itself, so the spin is going to change, you know, to some extent as well, and all of this can be calculated in physical way. I mean, the orbital angular momentum is the same as energy, but the spin itself.
I just wonder to a significant amount of things. Wire and wire. Sorry.
So my impression here is that the mode doesn't really nothing, but still, yeah, it's a large effect, but it's not that large. Non-linearities. But it'd be great if we had to worry about non-linearities. More to it, more handles on the internal structure. It's not so more complicated, but.
How much does, I guess, the amplitudes and this dephasing depend on the internal dissipation of the modes?
So, yeah, so that's something that can play a role, except that, so there's already dissipation present in the form of the initial gravitational waves. So,
Is that just
so
dominating?
that's why you drive across a resonance, you don't stay at resonance. So that's the main source of dissipation. The mode itself will dissipate, I mean, depending on the internal source of viscosity inside a neutron star, you would have to estimate this. So that will add on top, but I don't think that's going to be very significant compared with.
But the actual driving across resonance is determined by the gravitational wave. It's not by the.
But could you just probably word it right then on the spectrum? The driving force. How does that scale with the orbital frequency and with this frequency? Just, you know, overall sort of must be some power loss here.
So it doesn't scale the frequency. I think it's independent of frequency. The leading order,
Let's do the Gravitomagnetic effect is proportional to the orbital.
oh, orbital, yeah. So you can think of the tidal force as something that.
So it's a linear and orbital frequency.
Yeah.
And it doesn't have any dependence on the spin frequencies.
That's what I think, yeah.
Linear in order.
No, it's not linear, it's linear in the orbital velocity. If it's a B cross. So
Yeah.
the B field is linear in velocity, and then it's a B rotational times the orbital effect divided by 6.
Maybe this is what Chris was driving at, but if you can basically take all of your modes and different how you spin the star with your path. It's a omega of the star.
Yeah, I mean, there will be an action like this, but I think it's wrong to say. But now I realize I answered you wrong because the B field is proportional to both velocities, orbital and rotational. And so that will scale with both.
So do you then have a non-linear tidal frequency or non-linear dependence of the tidal frequency on the orbital and the spin frequency? Because normally I think of the tidal frequency as just the difference between those two.
Say again, please.
Normally I think of the tidal frequency as involving some difference between the spin frequency and the orbital frequency.
Right.
You have a
yeah,
non-linear
so-
dependence in your
Yeah, so depending on whether you work in a co-locating frame or.
right, yeah, or inertia.
Yeah, so, you know, ultimately there's going to be a back action mode on everything that might create some non-linearities, but you know, I think I don't expect, I might be wrong, but I don't expect that those non-inheritance will be very important. Because the linear effect is already,
Right, no, I didn't mean to say that the back reaction would necessarily be important. I'm not used to thinking of a tidal frequency as involving a nonlinear combination of the spin frequency and the orbital frequency. Is that the right way to interpret it?
right, and that's the nature of
Okay,
gravitomagnetic.
cool.
Yeah. So the inertial modes have technically scales. So if I have a slowly rotating star, the modes that you draw on your diagram basically swap on.
If it were very, so if you're not in a regime of 100 hertz or so,
Yeah.
if you use 10 hertz instead, then that's all. Way down.
So that would push where the modes become resonant to in spiral.
Yeah.
So they're separated. So the overall amplitude of the tidal problem will be lowered by some scale. So I think my question is, great, I'm glad that it's free. But I don't know what the scaling is and whether you win by sitting on resonance for longer earlier in the spiral, but with a lower. I know in the G mode case, like you said, that the overlap and go bad. So you just have to really need forcing, even though you sit on G mode time. That you have a high overlap with the scale. The orbital units. And you look at that.
So, yeah, so I think I want to rephrase the question would be, is this mode winning for that mode because it was running through resonance earlier in the spiral?
Well, so like, I think what I'm trying to ask is, would this effect be more important for more rapidly spinning neutron stars or slowly spinning?
So there's a scaling with omega that prefers large M. So yes, but that's But if you push omega so large, you would have to go to more accurate description of the mode beyond the order of omega. That the overall picture. But I think more importantly, once you fix the omega and once we agree that we want to work within that linear regime, I think it's still true that this mode will produce more of these things. But not that mode because it has longer, you should phase it for longer.
Yeah, I mean, there's a little kick and that kick. And so, but then the question is, when you go and this is the key mode that you right, it keeps getting smaller and smaller, the frequencies. So the difference is small.
Yeah, so there's a bit of a trade-off, but I think the skin will be, well, something about this.
So it's a perfect time to stop so we can continue discussions upstairs. Who's done?
Thank you very much.